Hello, we are IGEN Team 8 and our project is an assistive walking device for the visually impaired. We wanted to contribute to the biomedical landscape by creating a device that allows them to navigate the world with greater independence. Visual impairments are widespread, but the technology available is limited. White canes are most widely used because they are effective, accessible, portable, and inexpensive. Guide dogs and new technologies such as Weed Walk are inaccessible for many people due to things like costs and logistics. Our initial idea was a white cane attachment that uses ultrasonic sensors for object detection and haptic feedback for the user. However, we spent time conducting a total of 11 stakeholder interviews, 9 of which were potential users. We realized that users wanted guidance and reassurance for walking straight, and that simplicity is a priority. That means our assumptions were wrong. Users want a device that both helps them stay on a straight path and detects obstacles. A lot of people use Bluetooth earphones, so audio feedback makes more sense. They also want a device that complements their white cane rather than replacing it. Our solution is a wearable device that helps users walk straight using computer vision and uses an ultrasonic sensor to detect objects with a wearable device casing to tie things together. We set specific requirements for each of the components. At the end of our design process, we compared our final product against our requirements to gauge the success of our project. Our timeline was heavy on research and user interviews until early February, where we switched gears to implement the sensor and vanishing point detection. From late March to early April, we made the necessary accommodations due to COVID-19. The design portion of our presentation will describe in detail each of our technical elements and how we tested them. Our device features a 3D printed case attached to a crossbody strap with an additional security clip. The case will be printed in ABS, which is a 3D printing filament material that is durable, has wear resistance, heat tolerance, and prints fast. Our case will act as a protective housing for the electronic components, so it's important that it can withstand potential drops in hot environments. A base plate is permanently attached to the crossbody strap. When the release switch is pressed, it depresses the 4 locking feet. The device then slides into the base plate. Once the switch is released, the locking feet move up into slots on the base plate and hold everything in place. As we reassess our design after stakeholder interviews, we realize the advantages of wearable devices in the context of our project. To guide the user on a straight path, we use the camera. Unlike a white cane attachment, the stability of a wearable allows the camera to take steady images and is always in the same orientation as the user's body. This also eliminates any extra weight on the arm, causing less strain. Having both hands free gives more freedom to the user and can be used to complement the white cane. The attachment mechanism allows for quick and easy access to the case for charging or to be used as a handheld ultrasonic sensor. Since the case is 3D printed, we can make optimizations easily once we're able to build a physical prototype. The device also has a switch for selecting the range of the object detection and a USB-C port for recharging. The ultrasonic sensor and camera are mounted to the top of the case at an angle so that they will be horizontal when attached to a diagonal strap. The Raspberry Pi and battery are mounted at the bottom. The top part of the case is then secured to the bottom via screws that pass through each of the 4 feet as shown. Most of the components' weights were obtained from their specification documents. For the battery and crossbody strap, we estimated their weights by looking at options available online that would fit our requirements. We modeled the case in ABS and used SOLIDWORKS mass properties function to calculate its weight. The total mass was 294 grams, which is within our requirement range. This is a breakdown of the total cost of our project. 3D printing costs are reduced since the device is small. Our main costs were attributed to the electronic components. The total was $119, and we were able to stay well under our budget requirement of $200. There are 3 options we considered for mounting the device. The first option is a crossbody strap with an extra side strap. The second option features shoulder straps with the device placed in the center of the chest. The third option is similar to the first, but without the side strap. It is very important to us that the user is comfortable wearing the device. We used an ultrasonic sensor for object detection. To calculate distance, ultrasonic sensors transmit and receive sound waves. It can detect objects outside of a white cane's range, such as things above knee height and that are further than a meter away to provide reassurance of a clear path to the user. To test the individual components of our design, we used the Raspberry Pi 4 but used a much more compact Pi 0 for the final design. The MB1020 ultrasonic sensor's extended 6-meter range with a narrow 25-degree effectual angle was an ideal option to satisfy our requirements. To implement computer vision, we selected the Raspberry Pi camera module. When the device is on, The detection algorithm continuously measures the distance of obstructions. A rocker switch is used to select between a 4-meter mode and a 2-meter mode. Depending on this and the distance, 1 of 4 feedback sounds is played. In order to verify our 23-degree effectual angle and 4-meter detection requirements, we devised an experiment to check points in front of the user. Assuming the average shoulder width is 42 centimeters, we created a 42 centimeter by 4 meter rectangle, the virtual box. For example, at point 4-L, which is 21 centimeters left of the center line and 50 centimeters away, the angle relative to the center is negative 23 degrees. Repeating this process for various points, we verified our error to be less than 5 centimeters. Additionally, we measured the time from object detection to feedback to be much less than 1 second for both modes. Next is how we use computer vision to direct our users on the sidewalk. We do this by using a camera to determine the vanishing point of the path. For example, the vanishing point will be aligned with the center of the image if the user is walking straight, but will be to the right of the center if they're deviating left. We need computer vision for this, so here's our tech stack. Python is our programming language of choice since it complements well with Raspberry Pi and OpenCV, which is an open source computer vision library. For editing the code as a team, we use GitHub and Git, and Raspberry Pi uses a special Linux operating system known as Raspbian OS. Here's our image processing process. Using OpenCV's library of functions, we first turn the image to gray. Then, we do something called morphological transformations. This essentially groups clusters of pixels in your image that have very similar values. You'll see why this is important in just a second. Afterwards, we use an edge detection function to locate all the edges in the image. Now we can see the importance of morphological transformation. Without it, the edge detection detects a bunch of noise. While our eyes can see where the sidewalk is, the computer will mischaracterize the noise as a huge number of lines. We don't want this, so we use morphological transformation to clean it up. Next, we use Hough line transform, which takes the edge detected image and stores the lines it detects in an array for us to use. Here's the final result. Now we want to use the data from Hough line to determine our vanishing point. First, we create an imaginary grid overlapping our image. Then, using all those lines we found, we look for where there is the greatest density of intersection. That's most likely going to be your vanishing point. We look for where that point is in the grid, and now we want to provide feedback. So once the vanishing point is found, we find the angle between it and the origin. There's a threshold of acceptable angles whereby the user isn't deviating quite enough to be considered a huge problem. If they're too far off the threshold, however, feedback is given to the user. Piecing it all together, we use OpenCV to detect an array of lines, then determine the vanishing point and compare its angle to a threshold before finally outputting audio instructions to the user. In order to verify that our device meets the requirements for the vanishing point detection, we conducted 2 verification tests. First was an accuracy test to determine the success rate. This lets us determine if our device is reliable compared to what we can see. The accuracy was calculated by dividing the number of successful detections with the total number of images tested. A detection is considered successful when the actual vanishing point is within the computed vanishing point grid. For high-quality images taken with a smartphone, 8 of 9 were successful with a corresponding accuracy of 88.9%. For low-quality images taken with a Pi camera, 13 of 20 were successful with a 65% accuracy. The second test was measuring feedback delay. This helps verify a time delay until the feedback of under 2 seconds. Using the code, we calculated the time difference between when the image started processing to when feedback was provided. The average time delay is about 1 second for the high-quality images and is about 0.1 seconds for the low-quality ones. Combining the ultrasonic sensor and vanishing point detection results in a partially integrated product. When the device is on, both functions run simultaneously. The ultrasonic sensor calculates distance, reads the switch mode, and plays the corresponding feedback. Concurrently, the vanishing point code finds the vanishing point and angle. If the angle is greater than the positive threshold, audio plays in the left earphone. If it's less than the negative threshold, audio plays in the right earphone. From our integrated product, we were able to outline conclusions and future work. Looking at our requirements again, we satisfied all but one of them. We met our budget, and the device weighs less than 300 grams. Our device is configurable since it can be handheld but also has multiple strap options. With 2 modes, the ultrasonic sensor successfully detects objects 4 meters away with less than 5 centimeters of error. The vanishing point detection achieved greater than 80% success for larger images with 2 seconds feedback time. There are still some areas, however, where there is potential for improvement in future work. We could contact our stakeholders for physical testing, which we were unable to do under the current circumstances. A key limitation we discovered was the feedback occasionally glitching. We recommend using a stronger central processing unit to overcome this. This would also allow the use of more accurate computational methods to detect vanishing points, such as through neural networks in a wider range of environments. The user interface can also be developed to provide improved audio directions and allow the user to set up and configure the device through a mobile app. This concludes our presentation, and thank you for listening.